Welcome to Dr. Sherry's Astronomy channel. The theme this time is the discovery of many satellite galaxies in the Milky Way, exceeding expectations. When we think of galaxies in the nearby universe, we often imagine the stunning images observed by the James Webb and Hubble space telescopes. These galaxies consist of stars, gas, and dust, with dark matter surrounding them, and many contain massive black holes at their centers. The appearance of a galaxy varies depending on its components. When observed in near-infrared by the James Webb Space Telescope, stars appear as grains, while in mid-infrared, the distribution of dust becomes visible. In visible light, we can see the light emitted by stars and gas, but in regions with a lot of dust, the light is absorbed, making those areas darker. These large galaxies are thought to have formed through repeated collisions and mergers as the universe evolved. This is because, based on current observations, it is believed that the universe began around 13.8 billion years ago with the Big Bang. The Big Bang not only marked the beginning of space and time but also the origin of all the matter that makes up the present universe. Initially, everything was concentrated in a small point, but it rapidly expanded at an enormous speed, forming a huge gas cloud in which matter was almost evenly distributed. After that, the universe continued to expand, creating large voids in space, with thousands of galaxies clustered together in smaller regions, forming cosmic structures such as galaxy clusters. When we look at the nearby universe, we can see that galaxies are not distributed uniformly, rather, there are galaxy clusters where galaxies are dense, structures resembling lines connecting galaxy clusters, and filaments, which are part of the large-scale cosmic structures. Additionally, observations of the cosmic microwave background radiation have shown that, during the early stages of the universe's formation, dark energy constituted about 68%, dark matter about 27%, and ordinary matter, or baryons, about 5%. These observations have led to the establishment of the standard cosmological model of the universe, which is based on cold dark matter and the cosmological constant. The structures observed in the current universe, such as galaxies and galaxy clusters, are believed to have formed from fluctuations in the density of dark matter. These density fluctuations already existed when the universe was born, and they are thought to be observed as temperature fluctuations in the cosmic background radiation. The density fluctuations in the early universe had larger variations on smaller spatial scales, and the nature of these fluctuations changes significantly depending on the type of dark matter. Dark matter is broadly divided into hot dark matter and cold dark matter. Although they are referred to as hot and cold, this does not refer to temperature but to the speed of motion of particles with mass. Hot dark matter is made up of particles such as neutrinos, which move at speeds close to the speed of light. Cold dark matter, on the other hand, consists of much slower particles than light. The type of dark matter that dominates the universe affects how the cosmic structures form. If hot dark matter dominates, small-scale fluctuations disappear due to particles moving at light speed. This means that the formation of cosmic structures would start with the largest structures, like superclusters, which would later split into galaxy clusters and galaxies. In contrast, if cold dark matter dominates, small-scale structures would form first, and through repeated mergers and collisions, larger structures like galaxies, galaxy clusters, and superclusters would form. When we simulate the formation of these structures using the widely supported cold dark matter model, we can observe how small-scale structures grow larger over time. The Z represents redshift, with higher values corresponding to earlier times in the universe's history. The present universe is represented by Z equals 0. It is predicted that galaxies like the Milky Way contain hundreds to thousands of clumps of dark matter, and many dwarf galaxies are expected to surround the Milky Way. For example, as shown in the results, numerous dwarf galaxies form around a central large galaxy. However, in reality, the Milky Way is known to have only around 20 satellite galaxies. The significant discrepancy between theoretical calculations and actual observations is known as the missing satellite problem. So, why are dwarf galaxies so hard to find? As the name suggests, they are extremely faint and do not have a specific shape like spiral or elliptical galaxies. They show various appearances. Some dwarf galaxies seem to only have stars densely packed together, making them very difficult to detect. Additionally, the dwarf galaxies around the Milky Way are not biased in any particular direction, so a wide area survey with high sensitivity is needed. This is where the Subaru telescope comes into play. One of the key features of the Subaru telescope is its much wider field of view compared to other 10-meter class ground-based telescopes, the 30-meter telescope currently under construction, and the cutting-edge James Webb Space Telescope. The observation instrument that makes the most of this feature is the Hyper-Suprime Cam, HSC. The HSC is a massive camera with 116 CCD chips that together form an array of 870 million pixels, allowing it to capture a sky area equivalent to 9 full moons at once. This capability allows for highly sensitive surveys of wide areas of the sky. From 2014, a large-scale survey project was conducted, investing over 300 nights of observation over 5 years. The area observed in the large-scale survey project is shown here. The x-axis represents right ascension, and the y-axis represents declination. The region in the northern sky with declinations larger than -10 degrees is shown. The surveyed area is marked by the red line. Although the field of view is large, observing the entire sky is extremely difficult, so only specific regions were observed. Based on the vast amount of image data obtained, a research team consisting of members from the National Astronomical Observatory, Tohoku University, Hosei University, and Princeton University identified 9 new dwarf galaxies. In June 2024, 2 newly discovered satellite galaxies were highlighted with red and blue stars. Previously discovered satellite galaxies are shown in black squares. Looking at the images of the newly discovered dwarf galaxies, we can see one found in the direction of the Virgo cluster. The stars belonging to this dwarf galaxy are marked by white circles within the yellow dashed lines. We also discovered that this newly found dwarf galaxy is located more than 300,000 light-years away from the solar system. The 3D distribution of satellite galaxies around the Milky Way is shown here, with the center of the Milky Way taken as the reference. The plane of the Milky Way's disk is treated as the horizontal plane. The blue squares represent the Large Magellanic Cloud and Small Magellanic Cloud. Red circles represent other satellite galaxies, with smaller sizes indicating lower absolute visual magnitudes. The research team compared the number of newly discovered satellite galaxies with the number predicted by standard cosmological models. According to the latest theoretical calculations by the research team, around 220 satellite galaxies are predicted to surround the Milky Way. Considering the survey area and observational sensitivity, the expected number of satellite galaxies detectable by the Subaru telescope is between 3 and 5, which is about half of the number actually discovered. In other words, before Subaru's observations began, the problem was the shortage of satellite galaxies. However, now, the problem has shifted to one of having too many. The reason behind this shift is thought to lie in the basic physical processes governing how stars form and galaxies evolve within the dark matter clumps present at small scales. To explore this cause, understanding the distribution of dark matter within the satellite galaxies is key. A research team led by Dr. Vitrel from the Space Telescope Science Institute in the U.S. used 20 years of Hubble Space Telescope observation data to study the dark matter distribution within the Draco dwarf galaxy, one of the satellite galaxies. Although dark matter cannot be directly seen, it influences the motion of stars, which are visible. By measuring the three-dimensional motion of stars, the distribution of dark matter can be inferred. While it's easy to say three-dimensional, astronomical observations only provide two-dimensional images. Therefore, the research team used the Doppler effect to measure the velocity in the line of sight. By combining the two-dimensional movement of stars with a line of sight velocity from the data obtained over 20 years by the Hubble Space Telescope, they were able to precisely measure the three-dimensional motion of stars. As a result, for the first time, they were able to measure the three-dimensional motion of stars in a satellite galaxy, revealing that dark matter is likely to be concentrated at the center of the galaxy. Using this new method, the distribution of dark matter in other satellite galaxies is also expected to be determined. The data necessary for such analysis will be obtained by NASA's flagship space telescope, the Nancy Grace Roman Space Telescope, which follows the James Webb Space Telescope. While much attention is being paid to the distant universe thanks to the James Webb Space Telescope, the study of nearby galaxies for testing the standard cosmological model remains equally crucial. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.